All right, bring your homework if you haven't done that already. So I didn't post any videos for you to watch between Tuesday and today, first of all, because I didn't feel like making one. And also, what I'm going to do is either today or tomorrow, I'll make a video for, starting where we leave off today, and that way you'll have the whole weekend, if you want to do chemistry on the weekend, to watch it. And then on Tuesday, we'll do the last third, or really the last quarter of the content. And then the exam will be the Tuesday after that, after fall break. Yes? Yes. Yeah. Also on the homework, the only ones that you have to do and turn in are the ones that are bold and with the asterisk. But there's a lot of extra practice because that will help you, I think, especially in this chapter. Okay. So we talked a lot about aromaticity. We talked a little bit about reactions that happen right next to the aromatic ring, like at the benzylic position. But in this chapter, we're going to talk about reactions actually on the aromatic ring. So you might remember just from sort of previous chemistry that if you take benzene and you try to react it with elemental bromine, you might think, okay, usually when we add bromine to compounds that have a double bond, we do an addition reaction. But that's not going to occur in this case. So if we just do this as it's written here, we're going to get no reaction. But if we add a small amount of iron metal, whether that be in the form of iron filings or iron powder or something like that, we will get a reaction. And it's not one that you might necessarily expect. We get that, which you'll notice is actually a substitution, not an addition. I mean, it is called aromatic substitution reactions. Okay, so this is good because we still have an aromatic ring, and that's good because breaking an aromatic ring is fairly strongly disfavored. We're going to do it in just a moment here, but this is a better reaction than substitution, results in a lower energy product. So the sort of general mechanism that this goes by is called electrophilic aromatic substitution. Electrophilic. Or just EAS. And it's got three sort of main steps, which involve a couple different arrow pushing operations, but we'll get there in a second. The first is we have to generate a really strong electrophile. So in this case, the benzene is going to act as a nucleophile, and that seems kind of weird. It doesn't look particularly nucleophilic. It doesn't have a lone pair or a negative charge or anything like that. And it's true that it's not a very good nucleophile. And so in order to get that to react, we have to give it a very strong electrophile to attract it. So that's the first step. We have to generate a really strong electrophile. The second, and I just told you that this is a substitution, not an addition. Psych. We are actually going to do an addition. So you're going to do an addition reaction with the electrophile. So add electrophile. And also, we're going to break aromaticity. Again, breaking aromaticity is, that's better. Breaking aromaticity is generally unfavored, but if we've got an electrophile that's strong enough, we can kind of get away with it. And the third step is we're going to do an elimination reaction. We're going to eliminate a hydrogen atom and regenerate aromaticity. Okay, so let's actually go back and look at the sort of classic addition reactions to alkenes. So if we have cyclohexene, and we can do an addition reaction here with bromine, that's going to give us that. The nucleophile is our pi bond. And the electrophile is the bromine, specifically one of the bromine atoms of diatomic bromine. But anyway. And so we have to generate a strong electrophile. Well, this is not strong enough on its own to react with benzene, as is evidenced by the fact that that reaction does not occur. Ugh, sorry. And as it turns out, right, when we add iron to the reaction, it works. And so that is the role of the iron. It increases the electrophilicity of the bromine. Okay, so how does that occur? Well, first, actually, what happens is not really related to organic chemistry, and we have the iron metal reacts with the bromine and forms iron 3 bromide. Another thing you can do is you can just add iron 3 bromide if you happen to have some. You can add that to your reaction, and that's just the same as adding the iron metal. That's what we'll end up doing in the future. But we form iron 3 bromide. And then the iron 3 bromide reacts again with some bromine, and this is an equilibrium reaction, but doesn't particularly matter in this case. And we're going to form an interesting complex with kind of a bizarre structure. So sorry, negative charge there. Okay, so this is just the Br2 from the bromine attached to the FeBr3. And the advantage of this is the iron is essentially pulling all of the electron density toward the right, and so that bromine atom there is extremely electrophilic. So this is the actual species that is going to react with the benzene. All right, so how does the arrow pushing work for this? So notice I'm saying halogenation, because it turns out you can do this with chlorine as well. But anyway, so the first step, generate our strong electrophile. Okay, so this is the step that I just showed you, but let's draw it out with some arrow pushing. So we take our elemental bromine, Br2, and we have the iron bromide catalyst, and we simply have the bromine, one of them, attack the iron, and then we're going to form that bizarre complex, but I'm going to draw it out slightly abbreviated. Like so. Okay, so there's our super strong electrophile. Okay, so the second step is to add the electrophile and break aromaticity. So I'll draw out our benzene ring like that, and I'm also going to explicitly draw one of the hydrogens. Now that ends up being the hydrogen that is substituted when we do the substitution reaction. So we're going to take there's our iron bromide. So the bond that we're going to form is between this carbon and that bromine. And the electrons we're going to use to make it come from the pi bond here. So I'm going to draw an arrow like that. And like that. So the result of that reaction those two pi bonds are still there. There's the hydrogen that was attached. The bromine has been added, and pi bond has left that carbon. So there's a positive charge right there. In addition, we've got what's left over from that, just that ion. So this molecule, we call this the rhenium ion. And this is good because it's resonance stabilized. So normally breaking aromaticity like this would not be a good thing. And it's not super favorable. But because we can draw several resonance structures of that ion where the positive charge is delocalized throughout the ring, that is, this breaking of aromaticity is sort of okay. All right, third step is to eliminate hydrogen and regenerate aromaticity. So we have our rhenium ion. And we're actually going to use our iron bromide thing to do this elimination. So we're going to make a bond between the hydrogen and the bromine. HBr is going to be one of our products. And additionally, the important part kind of for the elimination is this bond that was previously to the hydrogen comes down, and there we go. Now we've regenerated aromaticity, gotten rid of the carbocation. So our side products are going to be HBr that we formed, and we're going to get our iron 3 bromide back. I should note that this also works with chlorine. But not fluorine or iodine. So the way we do it with chlorination, add Cl2, and the catalyst we usually use for this is aluminum trichloride. Questions on that mechanism? So this is really pretty much the only mechanism you have to learn in this chapter. It's going to come up frequently, but with different electrophiles other than bromine. Of course, you can use chlorine, but we're getting ready to talk about some of the other electrophiles that you can use for this as well. Yes?
one for number 3 and then also where is the HBr and the HCl?
So when we do this elimination here, this bond forms between the hydrogen and the bromine, and then this bond goes away, so we just have HBr. So that's the HBr. And same happens with the chlorine. We would have a chlorine here and the aluminum here, and that forms HCl. Okay, so classes of EAS reactions, we just talked about halogenation, which gives us that. We can do sulfonation to install an SO3H group. Nitration is going to be really important. Then there's alkylation. Can put on some sort of alkyl group there. And then there's acylation, which is slightly different. We install an R group with a ketone like that. Okay, I've just about exhausted my ability to lecture. So what I'm going to do is, in my video, I'm going to start with the next reaction, which is sulfonation. And I'll talk about these 4 reaction types. And then on Tuesday, we'll talk about putting everything back together and doing some synthesis problems with that information. All right, so sorry, but I will finish everything else on the video, and I'll see you on Tuesday. Yes?
First, I hope you feel better. Is it possible you can post the answer keys for what we do? Because it's really hard when you finish the packet, like the day of the exam, we turn it in, but we don't know if we actually got the question.
Yeah, I especially with the ones being due on the exam. Yeah, just send me what answers you have, just so I see that you've done it, and I'll send you the answers.
Okay.
Yeah.